These next couple of rules involve determinants of invertible matrices. This one says that a square matrix is invertible if and only if its determinant is non-zero. And this one says if A is an n by n matrix, or n by n invertible matrix, then the determinant of the inverse is equal to the reciprocal of the determinant. And the book goes through a nice proof of both of these things, and I want to give you a little bit of flavor of the proof. Let's look at this one first. If a matrix is invertible, then its determinant is non-zero. Okay, here's the general idea behind that. If A is invertible, then we know a couple of things. We know that A inverse exists, and by the definition of inverses, we know A times A inverse is going to give us the identity matrix. All right, now we've already seen that we can take the determinants of these. Now, the determinant of an identity matrix is always going to be 1, because it's a diagonal matrix, and you just multiply those ones together, and the determinant's going to be 1. So if I take the determinant of both sides of this equation, what I get is the determinant of A inverse is equal to the determinant of the identity matrix. And we know the determinant of the identity is 1. And then we can split this into the determinant of A times the determinant of A inverse equals 1. And there's no way either of these can be 0. If either of these were 0, then you'd have 0 times something equals 1, which is impossible. So these can't be 0. And then for the other direction, if you wanted to start off with the determinant as non-zero and show that it has to have an inverse, the general idea there is if the determinant is non-zero, then it'll row reduce to the identity matrix, and our algorithm for finding the inverse will work. So the full proof of this is on page 122 of the textbook. But let's look at this down here. We can use this for something like this. Is this matrix invertible? Well, you could try taking the inverse, or we could take its determinant. So this is a 3 by 3, so let's use our quick method for 3 by 3s. All right, when I do my 3 front diagonals, I get, let's see, 2 plus 0 plus 20. And when I do my 3 reverse diagonals, I get, let's see, 16 times 2 is 32, minus 3, and then minus 0. So what is that? That's 22 minus 32 is negative 10, minus 3 is negative 13. That's non-zero, so it is invertible. So I guess the answer to the question is yes, that thing's invertible. All right. This other thing says the determinant of an inverse matrix. If A is an n by n invertible matrix, and then the determinant of its inverse is 1 over determinant of A. And the proof for that is very similar to the thing we just saw. If A is an n by n invertible matrix, then we know that A exists and its inverse exists. And if we take the determinant of this, well, first off, before we take the determinant, we know if we multiply these out, we get the identity. If you take the determinant of both sides, you get 1. And over here you've got A, determinant of A times determinant of A inverse. You can just divide both sides by the determinant of A. And get that. Whoops. I triggered the scroll. And so that gives it to us right there. So this says Compute the determinant of A inverse using A from example 103. All right, so on that example up there, the determinant of A was negative 13. So the determinant of A inverse is going to be negative 1 over 13.